Hi guys, welcome back to my channel. I'm so glad to see you all here. So in today's video, we are going to talk about survival analysis and the data that we are going to perform the survival analysis on is the TCGA data that we will be downloading from the GDC portal. In this video, we will talk all things in terms of the concepts, the terminologies, as well as the idea behind survival analysis, as well as I will demonstrate how to perform survival analysis in R. So survival analysis is a statistical method used to analyze the time it takes for an event of interest to occur. So the idea behind survival analysis is to get the probability of survival over time. Time is a crucial element here as ultimately we are analyzing time it takes for an event to occur. So let's say we want to study the survival time of a group of cancer patients. We want to know how long it takes for patients to survive after being diagnosed with cancer and whether there are certain factors such as cancer stage or the age of the patients that affect the survival time. To start, we would gather data on a group of cancer patients including their age, their gender, cancer stage and other relevant factors. We would then follow them over time, tracking how long they survive after the diagnosis. As time passes on, some patients will survive while some will not make it or will discontinue from the experiment due to some other reason. We can then use this data to create something called as a survival curve, which ultimately gives us the probability of survival over time. We can use this curve to estimate the median survival time, which is the amount of time it takes for 50% of the patients to pass away. We might also use the estimate the 1 year, 2 year and 5 year survival rates, which tells us the percentage of the patients who survive at least 1 year, 2 years or 5 years after the diagnosis. We can also use survival analysis to identify factors that might affect survival time. For example, we might find patients that with more advanced cancer stages have shorter survival time or that older patients have shorter survival times than younger patients. Overall, survival analysis is a powerful method for studying the time it takes for important events such as survival or recovery to occur and for understanding the factors that might influence these events. So one important thing to know about survival analysis is that it analyzes the rate of occurrence of events over time without assuming the rates are constant. And when I say the rates are constant, it does not assume that the probability of an event happening in a given time interval is same for all individuals and remains constant over time for a given individual. So to give an example, if you are measuring the rate of recurrence in a particular type of cancer, survival analysis does not assume that the rate of recurrence is same for all individuals or it remains constant over time for a given individual. So in bioinformatics, when we are picking an analysis, it usually should help us answer the question that we are asking. So if the kind of questions that we are asking are like, what is the probability that a patient will still be alive after 5 years, or what factors influence the lifespan of patients with this disease or a particular disease that we are studying? Is there a difference between survival probabilities between two groups of patients who have been treated differently? So let's say if we want to see if treatment A is more effective than treatment B, or if we are trying to identify factors that contributes to differences in survival times between different subtypes in cancer. If we are trying to ask these kinds of questions, then performing survival analysis would make sense as it would help us answer the questions that we are asking and would ultimately give us the insight that we are trying to generate from the data that we have. One of the most important features of survival analysis is censoring. So it is important for us to understand what is censoring and why is it important. So censoring is basically a type of missing data problem, and let us understand more of it with an example. So let's say we start following a group of 100 patients from the time of the diagnosis of cancer, and we follow them for 5 years, and during this time 60 of them do not make it, that is they die from the disease, and 10 patients drop out of the study before the end of the 5-year period, and we do not know whether they died or not. There could be various reasons that these 10 patients discontinued from the studies, and the reasons could be that they simply dropped out of the study, or there is a loss of follow-up, or maybe they experienced a different event that made further follow-up difficult. So let us understand censoring more and how exactly it's performed with the help of an example again. And here, looking at the diagram, here we can see that in this example study, there are 3 patients, patient A, patient B and patient C. Patient A experiences death before the study ends, and we count this as an event. Patient B survives and passes the end of the study, and patient C withdraws from the study. Patient A requires no censoring since we know the exact survival time, which is the time until the death. Patient B, however, needs to be censored, which is indicated by this plus sign, since we do not know the exact survival time of the patient. We only know that they survive up to at least the end of the study. Patient C also has to be censored since they withdrew before the study ended. So we only know that they survive up to a time they withdrew, but again we don't know the exact survival time of the patient. Since patient B and patient C has not experienced the event, that is death, we will have to censor data from these patients and take that into account when we are calculating the survival probabilities. So the overall idea behind censoring is that some individuals in the cohort or in your data set might not have experienced the event of interest yet, and the full duration of the event is unknown for these individuals. As a result, the estimated survival probabilities and hazard rates may be biased if censoring is not taken into account. Since we've spoken a lot about events, it would be important for us to understand what is considered as an event. So, death, progression of a disease, relapse in case of cancer, development of secondary malignancy, or hospitalization, and all of these can be considered as events in context of medical research. There are various methods one can use while performing survival analysis. The first is the Kaplan-Meier curve, which is basically a graphical representation of survival function. And these are the curves that you might have often noticed or visualized when talking about survival analysis. Basically, it is a non-parametric estimate of the survival function that does not make any assumptions about the underlying distribution of the data. And Kaplan-Meier curve is used to estimate the survival function from the data that are censored, truncated, or have missing values. It basically shows the probability that a subject or an individual will survive up to a time t. The other method is the log rank test. It basically compares the survival times of two or more groups, and the null hypothesis for a log rank test is that the groups have the same survival. The formal test is based on the chi-square statistic, and when the log rank test is statistic is large, it is evidence for a difference in the survival time between the groups. Kaplan-Meier curves and log rank test are useful when the predictor variables are categorical or takes a small number of values. But if we have quantitative predictors like gene expression or white blood count or age, then we can use a method called Cox proportional hazard regression, which basically helps us to describe the effect of variables on survival. So Kaplan-Meier curve is a commonly used graphical representation of the survival data, which shows the probability of an event, that is survival at a certain time interval. So let us understand how to read this Kaplan-Meier curve, and there are some key aspects to interpreting this curve. So on the x-axis we have time, and the time can be in days, weeks, months, or years. On the y-axis we have survival probability or the percentage of of survival. This could be the percentage of the patients or the subjects that we are trying to study that have not experienced the event of interest at a given time point. The survival function, the curve itself is the represents the survival function, which decreases over time as more individuals experience the event of interest. The steps in the curve consist of the series of basically represents a point in time where an event occurred, such as death or progression. The height of the steps indicate the proportion of individuals who have not experienced the event up to that time point. So here I think at the second time point we can see a step up to 90%. So it indicates 90% of the patients have not yet experienced the event at this time point. The censoring, the curve may also have these sticks. So basically there are some patients that are going to have to be censored as they haven't experienced the event yet. In these cases, the actual survival time for these patients are not known, but the individual is still included in the analysis up to the point of censoring. So the tick mark on the curve represents the time at which the censoring occurred. So basically this curve is very useful in, for example, in terms of determining the median survival probability. So we could get the time at which 50% of the patients will survive. It can also help us if we have more time points. We can also determine the 1 year, the 5 year or the 10 year survival probabilities. If we also have two groups, data from two groups, we could compare the survival probabilities between two groups to determine if the survival probabilities between the groups are significantly different. So this was just a quick walkthrough on how we read the Kaplan-Meier survival curves and how we determine and gather various information from the survival curve. So for today's demonstration, the question that we will answer using survival analysis is, does high expression of TP53 influence prognosis in breast cancer patients? The data we will be using today is from TCGA, which we will download from the GDC portal using the TCGA Biolinks R package. So essentially there are three main things are required to perform survival analysis. The first is the time to event. So here the event is death. So I will require time until death for every patient. The second is status, where I will indicate which patients have to be censored and which will have to be considered for the analysis based on the time to death I have for the patients. For the patients that have not yet experienced the event, those will have to be censored out. And lastly, I will need event information. That is, since I'm interested in understanding whether high expression of TP53 influence prognosis, I will have to divide my cohort into high expressing group versus low expressing group. So event would be a variable where I will define whether this patient belongs to the high expressing TP53 group versus, or whether it belongs to the low expressing TP53 group. So these are my requirements for today's demonstration. I will use TCGA Biolinks package to download the TCGA breast cancer data from the GDC portal. The next two packages are to perform survival analysis as well as to plot the survival curve. Summarize experiment to get my gene expression data in a summarize experiment object, and tidyverse to manipulate the data. So this is our R script, and let us start by loading our libraries first as usual. After loading the libraries, the first thing that we're going to do is we are going to get the clinical data for the breast cancer dataset from the GDC portal. And in one of the previous videos, we used a package called TCGA Biolinks to download data from GDC portal. So we will be using some of the functions from the TCGA Biolinks package to get the clinical data. Let us use a function called GDC query clinic, which will directly give us the clinical data associated with a project name. So the project name here is TCGA BRCA, and I'm going to store the clinical data in a variable called clinical BRCA underscore BRCA. Now that the clinical data has been fetched, let us click on this clinical underscore BRCA object. And here we can see there are a bunch of clinical information associated with all the patients in this cohort, which includes the stage, the 8 days days to diagnosis, last known disease status, the tissue or the organ of origin, the days to last follow-up, age at diagnosis. There are like a bunch of information, clinical information that is associated with all these patients. We can see that there are 70 columns that are present in this object. So what we essentially want to do is we want to find out whether the columns that will be useful for us, if since we want to perform the survival analysis, there are particular columns of our interest, and we are interested to see whether the data has that columns present. And if yes, then we would want to essentially subset only those columns so that we can further use them in our survival analysis. So first, let us find out whether these columns are present in this clinical object. So let us use any functions to find these column names in clinical BRCA. Do these columns have any of these values? That is vital status, days to last follow-up, and days to death. I will tell you how we will be using these columns, basically the information that is stored in these columns. But right now I'm just interested to know whether these columns exist in our clinical object. And this returns true. So essentially I would want to extract which of these columns. So basically what are these column numbers? And essentially I would just want to extract those columns. So I'm just going to repeat the same command, but instead of any, I'm just going to use the which command, which will give me the column, which will just give me the indexes of the matches. And so it's apparently column 9, 39 and 45 that matches to these values in the clinical BRCA object. So let us just quickly take a look at these columns. So here we can see that we have sort of extracted these 3 columns, and this is the days to last follow-up, this is the vital status, and the days to death. Since we have vital status available, I am just interested in knowing how many of these are alive and how many of these patients are dead. Just taking these numbers, just getting these numbers using the table function. So using the table function, we can just quickly get these numbers. So apparently there are so many patients that are alive in this cohort and there are so many patients that are dead. So before I move ahead in this analysis, recall how we discussed we need 3 things to perform survival analysis. We need the time information, we need the status information, and we need the event information. So first, talking about the status information. We priorly discussed how censoring is important, and we need to censor those patients in our cohort which have not yet experienced an event. So in our cohort, there are some patients that have not experienced an event, that is death, and we need to censor those patients out. So we can censor those patients out by creating another column in our clinical BRCA object. So I'm going to create a column called deceased, and I'm going to assign false value to all the patients that are yet alive. So I'm going to write an if and else statement here, and if the vital status is true, is alive, then I will set this value as false, or else I will want the value to be true. The patients that have experienced the event, that is the ones that are dead, I want the values to be true. So I will set the status, and this is the deceased column is essentially my status, which I will be using in my survival analysis. So let us quickly check the deceased column in our clinical data file object. And here you can see that the ones that are alive have been assigned the false value, and the ones that are dead, that has experienced the event, are assigned as true. Now that we have status information for each patient, the next thing we need for survival analysis is the time. So here there are 2 columns essentially, the days to last follow-up and days to death, which will help us create an overall survival information for each patient. So basically days to death would be the number of days that passed from the initial diagnosis to the patient's death. And days to last follow-up, that is that would be the number of days that passed from the initial diagnosis to the last visit. So the patients that are yet alive will be assigned the days to last follow-up days, and the patients who are dead would obviously be having the time that is recorded until the death. So basically, let's create another column called overall survival. And again, let's write an if and else statement. So if the patient is alive, using the vital status information again, then I want this is alive. Then my overall survival should reflect days to last follow-up. And if this is false, that is if the patients have experienced an event, then I want the overall survival to reflect days to death. Okay, so now that we have the status information and the time information, the third thing is the event. So here we are trying to compare the survival probabilities of 2 groups of patients, one group having high expression of TP53 and the other having low expression of TP53. Now, in order to sort these patients into 2 different groups, we will need gene expression data. And once we have the gene expression data, then we can look at the TP53 expression and decide which patients have high TP53 expression and which one has a low TP53 expression. So in order to decide that and to get the final piece of information to perform our survival analysis, we need to download gene expression data. So we will be downloading gene expression data using the GDCquery function from the TCGA biolinks package, and essentially we are building a query here to get the RNA-seq quantifications. This is something that I had previously explained in one of my previous videos where I was demonstrating TCGA Biolinks package and how to download data from GDC portal using that package. I will add the link to that video in the description section below. So here, not going much into the details of how to build a GDC query, here I'm mentioning the project, the data category, the experimental strategy, the workflow, the data type, and the sample type. And currently I'm interested in only primary tumors. So I'm specifying the sample type to be primary tumors, and I want the data to have open access. So let us run this GDC query. So now the query has finished running. Let us use the getResults function to store the output of the query into an object as a data frame. So here we can see that the output object has retrieved all the files and information corresponding to our query. And here we can see that this is a very large cohort. So let us just subset and only get the barcodes or information about the cases for only 20 of the primary tumor tissues or the tumor cases. So let us get only the barcodes for we can so when I say barcodes, we can provide the specific cases that we want to download, and we can get the cases names or the IDs of the cases from the cases column. And since this is a large cohort, I don't want to download so many of the files. I just want to get like 20 something primary tumors and perform my survival analysis with only 20 cases for this demonstration purpose. So here I am going to match all the rows that have sample types primary tumor, and I'm interested in the cases, and I'm just interested in the first 20 cases. And let us save this to a variable called tumor. So when we look at this tumor variable, we can essentially see the case IDs of all the patients or the primary tumor cases. And essentially I want to download only these data associated with these 20 cases. So let us build the query again. So I've already written the query. It's the same query as I had above. The only difference being that here I'm going to specify barcode, and here I'm going to provide the tumor. So basically this is a vector containing my all 20 primary tumor cases that I want to download the data for. So let us run this now. Now that my query has finished running, let us download the data using the GDC download function. You can see that there is additional folder being created in my working directory called the GDC data, and within this has nested folders, and in which we can find the data for each of our 20 primary tumor cases. Not going into the details of that, as we have spoken about this in detail in the TCGA Biolinks video where I was demonstrating the package, so not going into the details of that in this video. Now that we have downloaded the gene expression quantification, we can use GDCprepare function to extract the data from the query and save it as a summarized experiment. So here I am saving the gene expression quantification as summarized experiment in TCGA BRCA_data object. And since this object has different types of quantifications available, I'm going to extract the unstranded counts and save it in a variable called BRCA_matrix. So when we take a look at this matrix, we can see that we have quantifications available for the 20 cases, and this is something that you will be familiar, where you can see the row names as the gene IDs and the columns are the cases that we downloaded the data for from the GDC portal. Now let us extract the gene and the sample metadata from the summarized experiment and store them as data frame. So let's extract the row data from the TCGA BRCA_data object and store this into a variable called gene_metadata. And similarly, let's extract the column data and store that as a data frame from the TCGA BRCA_data object. So before going ahead, taking a little pause and rethinking about the steps that we have performed so far, the whole idea behind downloading the gene expression data is because we are interested in finding whether there is a survival difference between patients having high expression of a particular gene versus low expression of a particular gene. And since the expression here is in question, we have downloaded the expression data. Now that we have counts data, we cannot use the raw counts to essentially determine a cutoff where we can bifurcate the group into patients having high expression of for a particular gene versus low expression for a particular gene. We need to perform variance stabilizing transformation on these counts to perform further downstream analysis and use these counts in order eventually to determine a cutoff for a particular gene of our interest and divide our patients into our groups of interest. So in order to perform variance stabilizing transformation, we will first create a DESeq dataset using the matrix, the count matrix and the call data. So we have the count matrix stored in the BRCA underscore matrix object, and our column data or the sample information is present in the call data object. And here for the design, we are not going to specify any design since we are just interested in creating a DESeq dataset. So let us create this dataset. And since I get thrown this error that could not find function DESeq from dataset matrix, I realize that I have not loaded the DESeq library and hence it throws me this error. So let us go quickly back to where we have loaded the libraries, and here I did forget to load the DESeq2 library. So let us first load this library and go back to where we are trying to create the DESeq dataset from the matrix, and let us rerun again to create a DESeq dataset. Now that our DESeq dataset has been created, let us perform some standard pre-filtering of removing genes which has less than 10 reads across all the samples. So let us remove the low expressing genes from our DESeq dataset. And once we have removed the low expressing genes, let us perform the variance stabilizing transformation. And we can simply use the VST function here to perform variance stabilizing transformation. This returns another summarized experiment object, so that is saved in VSD. And using the assay function, we can extract the variance stabilized transformed counts from the VSD object and save it to another variable called BRCA underscore matrix underscore VSD. So let us quickly take a look at these variance stabilized transformed counts. So basically, now that you can see that these are not whole numbers, these are some numbers with decimals indicating that these are transformed, variance stabilized transformed values. Now that we have the variance stabilization transformed counts, next I want to perform some data wrangling steps. So with this data, I want to change the shape of the data, and I want to add the gene symbols for these gene IDs. Since these gene IDs are not very informative for me at this point, I want to add the gene symbols. And once I add the gene symbols, I only want to retain data for my gene of interest, that is TP53. There are multiple ways to basically add gene symbols corresponding to these gene IDs, and I have previously created a video on how to convert these gene IDs to gene symbols. I will also add the link to that video in the description section below. But today I'm not going to use any of those methods because I already have the information of what these gene IDs, what the gene symbols are that correspond to these gene IDs in my gene metadata data frame. So recall how previously when we were extracting the original counts using the GDCprepare and we had the summarize experiment object, we did save the gene metadata information using the row data function. So let me show you what the gene metadata data frame has. So basically this gene metadata information has information about the genes, but my interest here is only to get the mapping of gene ID to gene symbols. So since I already have this data available, I want to add this data to my variance stabilization transform counts. So let me show you how we perform all these steps. So let us start with our BRCA matrix variance stabilized transformed counts. First convert them into a data frame. Then since my row names are the gene IDs, I want to convert my row names to columns. And give the column name as gene IDs. Now that these row names have been converted into a column, now I want to change the shape of the data. So I'm going to gather my data. So I want all the cases to be in a column called case IDs, and these values to be in a column called counts, and I want to exclude the gene ID column. So I'm just going to put a hyphen and write the column gene ID. So let me quickly show you how this basically looks like. So I'm just going to use a function called head and run. So now you can see that all my gene symbols are, or rather my gene IDs are in a column called gene ID column. All the cases, that is all these columns, are now in one column, that is my case ID. And all these counts that are corresponding to these genes are present in another column called the counts. Now that my data is in a more concise format, I want to add the gene symbols corresponding to these gene IDs so that I can subset this data frame to only have data for TP53. Now I don't know which gene ID corresponds to TP53. So I need to add basically this information, the gene symbols, to this data frame. And the way that I'm going to do that is that I'm going to merge both these data frames by gene ID columns, because that is the one column that has a commonality between both these data frames. So let us do a left join here. The dot here indicates that this is the first data frame that I'm using. The second data frame is gene metadata, and I want to merge it by gene ID. Let us quickly take a look at what that looks like using the head command. So now that you can see that we have all the information from the gene metadata added to the original BRCA data frame that we had, the BRCA underscore matrix underscore VST. So now we know which gene IDs correspond to which symbol. So now we can simply filter the rows using this gene name column. So let us filter these rows to only contain rows that correspond to TP53 gene. So let us also quickly take a look before we save this into another variable. So let us do a head here and see that now we have all the rows corresponding to TP53, which is the gene of our interest. And now since this is our desired result, let us store the output of this query or all these commands to another variable called BRCA TP53 object. So basically now you can see that we have information regarding the counts for all 20 cases for the TP53 gene. After having downloaded the gene expression data and performing variance stabilizing transformation and also wrangling the data to only retain the data of our interest, we next come to the meat of the problem, that is how to divide patient cohort into low expressing and high expressing groups. So there are several approaches that one can take here. The first and the most simple approach is to use a median value. So if a patient has expression or a VST count which is less than or equal to the median value, then a patient can be classified into low expressing group. And if a patient has VST count higher than the median value, then the patient can be classified into high expressing group. Another approach that you can take is using percentiles. So if the patient's expression value is below 25th percentile or is equal to or below the 25th percentile of the entire cohort, then the patient can be classified into low expressing group. If a patient's expression value lies somewhere between 25th percentile and 75th percentile, then the patient can be classified into the medium expressing group. And if a patient has expression value greater than the 75th percentile, then the patient can be classified into high expressing group. Another approach is using custom values. So if there is a custom value that one wants to choose based on a prior biological knowledge, or if a value that makes more sense based on the minimal expression level that is biologically relevant, then that value can also be chosen to divide the patients into lower the high expressing group for that particular gene. And lastly, statistical tests can also be used to determine the cutoff. So statistical tests like t-test or Mann-Whitney U-test can also be used to compare the VST counts between two groups of patients, and the resulting p-values can be used as cutoff to bifurcate the cohort. So today we are going to use the median value to bifurcate our cohort into high expressing versus the low expressing group. So let us calculate the median value using median function, and we'll simply calculate the median values for the TP53 counts. Now that we have our median value, let us assign which patients have greater than median expression and which patients have lower than median expression. So let us create another column called strata, and let's write an if-else statement. So if the counts are greater than or equal to the median value, then let us group these patients into high expressing groups. And the ones that do not have the expression greater than or equal to the median value, then let us group them into low expressing groups. So basically, when we look at the BRCA TP53, we'll essentially be able to see there is an additional column being added with patients grouped into low or high expressing groups. Now that we have three essential pieces to perform survival analysis, we have the time information, that is the overall survival for each patient. We have the status information, that is the patients who have experienced the event versus the ones that have not and they are censored. So we have the status information for each patient. And we also have the strata information for the patient, that is the event. So basically we wanted to compare the survival probabilities between the two groups, and we have divided our patients into two groups. So now that we have all the three elements to perform the survival analysis, let us compute the survival curve. But before that, let us put all the information into one data frame. So we have the overall survival and as well as the status information in the clinical_BRCA data frame. And we have the strata information in the BRCA_TP53 data frame. So let us merge both these data frames. Now I will want to merge these data frames by the case IDs, but you will see the case IDs represented in these data frames are different. So I might have to change the case ID in the BRCA_TP53s to get rid of these additional characters so that it matches the case IDs or the submitter IDs in the clinical_BRCA data frame. So let us perform these basic operations to change the case ID. So here I'm just going to use regular expression. So basically I want to remove everything after 0, 1 and whatever characters that follow after the 0, 1. So basically I just want to retain this first part. So I'm just going to write a regular expression and replace it by just remove it, replace it by nothing, and provide the column name here. So let us check whether our changes have reflected. So it seems to have done what we were expecting it to do. So now let us merge both these data frames by case IDs in BRCA_TP53 object and submitter ID in clinical_BRCA object. So let us merge. So in the first data frame, it is called case ID, and the second data frame, it is called submitter ID. So now that this has run successfully without errors, just making sure. So you can see that now there is clinical information also added to this data frame, and you can see in your global environment pane, you can see that this data frame has 84 columns. So in addition to the columns that were present in BRCA_TP53, all the columns in the clinical_BRCA has been added. So now that we have all the data combined in a data frame, that is the BRCA_TP53, let us compute the survival curve. So in order to compute the survival curve, we use the function survfit. And the first object or the first parameter that it takes is the survival object, which it can be created using the surv function. The first parameter of the surv function is the overall survival, that is the time. And the second is the status, that is whether a patient is alive or dead. And we then provide with a tilde, we provide the grouping. So here we are interested in comparing between the strata, that is patients having high expression versus low expression. And finally we provide the data, that is BRCA_TP53. And let us save the output of this function into an object called fit. Now let us look at this fit object to see what we get. So basically this fit objects gives us information on what were the strata that we compared, the number of individuals that were present in each of these strata, the events that were detected in each of these strata. So basically there was one event detected in high expressing group and 3 events detected in low expressing group. We also get median survival information. So for the low expressing group, the median survival were 999 days, but for the high expressing group it could not be computed. And these two columns provide us the lower bound and the upper bound of the 95% confidence intervals. So now let us plot this survival curve. So let us use ggsruvplot and provide fit object. We provide the data as BRCA underscore TP53. We want the p-values and we also want the risk table. And now let's run this. So zooming in on the plot here you can see that there is significant difference in survival probabilities in patients having high expression of TP53 versus low expression of TP53. So just to orient you to this plot, on the x-axis we have time, and here, since the time for us was recorded in days, these are the number of days, and this is the survival probability. And coming to the risk table at the bottom, the risk table basically shows the absolute number of the patient at risk at each time point. The survfit function that we used here is used to estimate the survival probabilities and to create Kaplan-Meier curves. But since today we are interested in comparing the survival probabilities between two groups, we would actually be using a function called survdiff. So the entire command remains the same. So survdiff also takes in the survival object, and we can provide the grouping variable, and we also provide the data. But instead of the survfit function, we should be using survdiff, and let's store the output of this function into another variable called fit2. And now let us take a look at the output of the fit2. So here we obtain a similar output to what we obtained with survfit, with some differences. So again, we get the number of cases or the patients that are present in both the groups, the high expressing and the low expressing groups. We also get the observed events in both these groups. And in this case, we also get the expected events, considering that there are no differences in these groups. So these would be the expected events that we would observe had it been that there was no difference in the survival probabilities in these groups. And these values here give us information on the contribution of each group to the chi-square statistics and the variance of the contribution of each group to the chi-square statistic. Here we have the chi-square statistic, the degrees of freedom, and the p-values. So if we want to compare survival between two groups based on a categorical variable, we should be using survdiff function. But if you just want to estimate survival probabilities and want to create a Kaplan-Meier curve, then we can use survfit function. We can also use survfit function, and visually we can add the p-values. But if you want to programmatically determine whether there is a difference in the survival probabilities between two groups, then we can use the survdiff function. So that brings me to the end of this video. I hope you found this video helpful and informative. I will upload my script to my GitHub repository, and I will be adding the link to my GitHub repository in the description section below. I will also be adding the links to the videos that I referenced in the video in the description section as well. So if you like this video, please make sure you hit the subscribe button, like the video, share it, and leave your comments under the comment section. Until next time, see you.